Good evening, everybody. Welcome to League of Extraordinary Inventors. I'm your host, Mike from Faraday Research. It is Free Energy Friday. Welcome to the show. It is April 25th, 2025. Welcome. We got our usual panel on. We got Ben in the background. We have Lulu.
How you doing, guys?
We got Lulu and we got Mr. Phillip on. Live chat is open. Any questions, comments for the panel tonight? Let's light up that chat tonight. And we got our usual crowd showing up to the show tonight, so that's great. And we'll get right into it today. I've been basically ordering parts for that off-the-grid project I'm doing it for a friend of mine. He wants me to build a unit that's in a box with wheels on it and a handle, and you can take it camping with you. So take it camping, you can use it and cook, your electrical devices on it, your induction cookers and stuff like that. And lighting and maybe a small heater and stuff like that. You'll have a solar panel with it. So I'm just piling up all the parts here. The box is supposed to be coming in Monday, so I hope Monday I get the box. I had to order it from Home Depot, but I could only get it online. So I have to wait for the shipping for them to ship it to the store. And then when it gets to the store, then they'll call me up and I can go pick it up. So a little bit of a waiting game, but I've got most of the components now. And I'll be starting that build soon. And I'll also be posting all the build videos. So we got Bernie out there. He says he's going to be joining us in about an hour's time. So that's cool. I want to start the show with a video first, and then we're going to jump right into Phillip because Phillip is going to kind of carry on with this. And so basically years ago, back when J.J. Thomson and he was coming up with the electron and all this, Tesla had an issue with it. He didn't believe the electron theory. Now, speed up forward to 2025, I managed by chance to see this interview with Mr. Neil deGrasse Tyson and this physicist talking about the electron. So I want you guys to listen to this, and this kind of goes back to what Tesla kind of felt about the electron. So with a little bit more detail, with a lot more testing and engineering over the last 125 years, this guy seems to be quite on the mark with what he feels that the electron is. So I'm just going to do a screen share here. Okay, here we go. Can you guys see my screen?
Yep.
Okay.
Ask you a blunt question, which sounds stupid, but I think it's a meaningful question. Do electrons exist? As
now, wait, is that a science or a philosophical question?
Well, because
natural philosophy.
As I understand it, we have never measured the size of the electron. It is smaller than the smallest capacity we have ever conjured to measure its size.
Okay, I got to ask you a preliminary question. How truthful do you want me to be?
I love it.
Okay, give me what you say in the back room. In the back room with the cigars.
No, let's lie to me. Then tell me the truth.
Okay.
The lie is,
yes,
what is real is the electron field. And little vibrations in those electron fields show up in our detectors as particles. So it's not that we haven't measured the size of the electron, it's that there is no such thing as the size of the electron. The electron is a vibration in a field. It can have different vibrational wavelengths.
And it shows up as the particle.
Yes, that's right. Yeah, that's right.
I mean, it comes to the party that way, but otherwise it's not.
Yeah.
Okay, that is trippy.
Wait.
That is so freaky, man.
Wait.
So you and Einstein both were bothered by this.
Yeah, I am very bothered by this.
Wait, so you cannot measure the electron in its wave state to be a particle, because the act of measuring it turns it into the particle.
The way that we usually measure things, you say, where is it? and you get a little track in your particle detector because you keep asking where it is, and you always get a definite answer to the question, where is it? But when you're not asking that question, it's spread out all over the place.
Let me ask you a blunt question, which sounds.
So, what do you guys think of that?
Yeah, that's awesome.
Well, yeah, I mean, it's a point particle, like they call it, because it has. They can measure. They couldn't measure its radius.
Right, because it's a field. It's a coherent field.
Yeah.
Which creates a shape, and our detectors can detect it. And when you see it, it looks like a particle, but it's not. It's actually a field that looks like a particle, but it's not a particle. Yeah. So Tesla is very, very correct on this, saying an electron is not a particle energy. It is a field. And I think Farnsworth, the guy who created the TV, from what I heard in one interview with Eric Dollar, because he knew the Farnsworth family, Farnsworth knew what the electron was, but he never wrote it down, and he never revealed the secret on what the electron actually is. And I think it's pretty obvious now because so many years passed, right? We got better equipment, better detection equipment to prove that the electron is not a particle.
Yeah. Yeah, I wanted to say something, I forgot, but the electron, like I was saying earlier, it's some sort of, it's not like it's not like a ball of pool. You know, people think it's like a ball of pool, but that's not what it is at all. It's some side effect of a virtual particle that
it's waves. It's like
it's like a wave.
Yeah.
Same thing with the positron. And when the electron and the positron are entangled together, it creates a photon with kinetic energy. That's why it moves, like I was explaining a couple of weeks ago.
Right.
So, but because if you calculate the mass or the energy, the mass equivalent of a photon, it's if you wanted to split if you want the photon to split by the pair production, you need very high energy photon to produce an electron and a positron. So you have the proof right there. That's what the photon consists of. It's really a packet of energy, neutral packet of energy.
Right. Okay. So like what we were talking about before we went on tonight. So you have the electron. You have electricity. Okay. So according to Eric Dollard, and I've studied his stuff quite intensively for the last probably 10 years. You need, in order to create electricity, is what we call electricity. It needs two components: magnetism and dielectricity. With those two components combined, it becomes a hybrid, like he explains. And that hybrid becomes electricity. Now, also in that reaction too, when conditions are just right, it can emit a photon. So that means there's a component within the photon with the reaction with electricity will not only give you electrical power, but it will also emit light. So I think it's a combination of particles coming together at once to create either a photon or create electricity that emits a photon. So,
so the electron, positron, and photon, they're very similar. Now you're adding the dielectrics and the magnetism. I'm going to study that.
Right. So when you get the dielectricity and the magnetism, that's what we call electricity. Now, if it adheres or couples with anything that's a metal, like a metal wire. Now you've got the electromagnetic field now, okay? And because you got the electromagnetic field, any freestanding electron, I hate using particle because it's not. It's a coherent field of energy.
Yeah.
When you have a wire that's now magnetized with an electromagnetic field, any other of those particles, I hate using that are around the wire are now going to be coupled with that wire. And that's why we create an electromagnetic force around the wire, right? And the more of those virtual particles of electrons hitting the wire, going through a wire, and depending on the length and the diameter of the wire, that wire will now emit heat, right?
Yeah.
So
the resistance.
there's resistance in the wire, and the compiling of all those electrons on a very small area. And the more electrons that you get focusing in the magnetic field and being coupled with the wire creates your current. That's where all the current and the heat comes from. So I think I'm pretty close to the mark there on that, because it's you have to separate every single particle and its components and find out what the relationships are, what makes electricity, what makes a photon, right?
Yeah.
What makes an electron? What are those separate components when you put them all together that create what we call an electron or electricity or a light?
But I was studying voltage also a little bit this week. Voltage, yeah, we all know it's a difference of potential. It's joules per coulomb.
So the actual real definition of voltage is the rate of energy that is consumed by the circuit. That is actually came from Eric Dollard. I pounded that one into my head over and over and over again. It is the rate in which electrical energy is consumed by a circuit. That's what voltage is.
The rate, it's a voltage divided by resistance equals current.
Right.
So that's like a rate of energy that is consumed by the resistance.
By the circuit, right. Yeah. So it's the rate of energy that is consumed by the electrical circuit. That's what the quote-unquote definition of voltage is.
Yeah.
Right?
Wouldn't that mean like the circuit is different? Like it would... All right. I have an idea.
Because any electrical circuit, especially say like a coil wire, it has capacitive value, right? So you could store some actual energy in that coil. That's why you get all that coil in the back EMF coming back in that coil, because there's mass there, right? That's why Joseph Newman, he was making rotors that weigh 4 tons. And he was moving it with just voltage potential, not current. He had about 50 or 60 milliamps going through that circuit into a very large mass, such as his rotor that he made for his, what he called Big Eureka. And he was able to move, a 2.5 ton rotor with 460 volts DC at about 50 to 60 milliamps. So it's all voltage, no current. So the big question was, where was he getting the energy?
Yeah.
Inside the coil. Inside the coil, he was creating a huge magnetic field, which creates an electromotive force. When you have an electromotive force, it can do work. So therefore, all he needed was voltage. The current and the back EMF from the spiking of the spark gap while it's running creates that inductive reactance in the coil, giving it even more electromotive force in the coil that enables you to move a 2.5 ton rotor. Okay, so everybody's thinking, oh, Well, it's the power output that he was trying to get over unity. No, it wasn't the power coming out of the machine. It was the physical, mechanical power that he was creating. That's where the over unity was in the Newman device. It wasn't from the back EMF pulses that were coming out like a Bedini motor or whatever, or even like my motor. His gain was on physical motive force created by that rotor. You got a 2.5 ton motor and it's spinning at 400 or 500 RPM. Try to stop it with your hand. You couldn't do it. It would throw you across the room.
Yeah.
You have so much motive force there, 2.5 tons behind it, and you cut the power off and you try to stop it with your hand, it'll throw you right across the room in a second.
What's a 2.5 ton rotor used for? Like ships, big.
Oh, sure. Huge induction motors, factories might use them,
Okay.
but he was proving the point that he was able to get his over unity based on electromotive force. That's the actual torque of what the motor was able to create with a high voltage, but a very low current, right? So he got a small motor that was 12 volts DC, ran it off a car battery, okay, at full tilt. That little motor burned out within, I think it was 40 minutes, and it started to smoke, okay? But his big Eureka is running on those little tiny 9-volt batteries for over 5 hours before the batteries died. And to boot, the device he was moving with, those little 9-volt batteries, weighed 2.5 tons. So what's over unity? That little 12-volt motor with a car battery, or his giant rotor that weighed 2.5 tons? So it was pretty much conclusive that he had an over unity device. And the US patent office, he had the best engineers in the US test that thing. You had guys from MIT, US patent office. He had these high level electrical engineers with pretty much all the credentials you would want in an engineer, and they couldn't disprove his machine. They said it's doing what it's doing. And still, in federal court, they still denied him this patent. So that's the state of our world.
Yeah, I'll show you later that the academia, mainstream academia, they have way too much power over experimental physicists or experimental anybody, because we're doing this. I'll show you later. I already talked about it, but I'll remind people later that the experiments are not representing the predictions from the textbooks at all regarding the my liquid metal vortex that has a stronger force than what the textbooks are predicting, and I've got the exact same factor, the exact c square. It's the amplitude of the shift between the experiment and the academia is a factor of c square. So the academia is off by a large factor a lot of the time, and that includes the vacuum catastrophe. Also, that is a huge unsolved mystery that they can't explain still up to these days, and it throws off academia upside down, and the academia says, "Oh, it's no big deal." Of course, it is a big deal. It just overthrows your whole general relativity upside down, and you say it's no big deal. I mean, it's even if you prove them they're wrong, they're still gonna be
Yeah.
ongoing with their agenda.
Yeah, exactly. You're going to have a fight. Yeah. And that's to be
Yeah.
expected. That's what's been going on for the last 125 years. So
Yeah.
it's nothing new as far as I'm concerned.
Yeah, like I was saying the other day, since 1940, the peer review system started. They started peer reviewing journals like manuscript in a way that favors the conservative, not the political conservative, but the conservative mindset in the mainstream academia since 1940. So and it's every year it's getting worse. So imagine in 2025 how
Right.
bad it is. It's like exponential.
Yeah.
And
Yeah.
What they
yeah,
don't to factor with the academia that it's evolving. It's not just the same old classical method of what uh, uh, science is or researchers or scientists. Like they're stuck on the old way that they can't see that then like sometimes the stuff that we talk about is it gives them a topic to teach at school. You understand? It doesn't exist right now. This is so what is academia? They take it from somebody that actually experimented, got results, and then they somehow, manufacture it to a product that's called education for a degree, and then they, teach it to students. But things are timeline evolves, and you can't tell me that the teachers currently or professors are teaching things that are just based on old methods, because these students are going to at one point graduate and create their own.
no, it's not based on the theory is based on the old methods, yes, but not the equipment. They're very happy when they have new equipment in their lab and they're fine tuned. It's all specialized equipment, but the roots, the theory, the roots of their theory is it's completely outdated. They don't want to admit it's wrong, so they're very conservative in that sense.
Yeah,
I,
they're just trying to protect their funding and their
yeah, they
schools and
they
all that.
they
And
they create.
it's blocking the real science from progressing forward because they're worried about if their funding's going to get cut off or not because they're going
Yeah, exactly.
over a barrier.
So write them the new values. I mean, this is what, right? I mean, they're getting funding for equipment and they're testing these theories and they're coming out with something different. Then, like, why do they need the equipment if they're not going to publish what they find?
Well, they'll publish only what they need to publish.
Yeah, they
If there's
cherry
real
pick.
if there's real breakthroughs going on and it gets reviewed by, say, the professor of the laboratory, and he says, okay, this is going to cause us some issues where we could lose some funding here,
Yeah,
he'll stop you right there and say, okay, this is going to get pushed aside. We're going to work on this, and we're going to still say that we haven't figured it out yet.
yeah.
Therefore, we know that next month's paycheck is coming in.
It's not like that in all department of the academia. Computer science is not like that at all. But that's theoretical physics. They for some reason they chose that field to block, probably because it is the most powerful. I think if we unblock theoretical astrophysics, then we will move forward and pretty fast. And if we convert theoretical astrophysics into what computer science is right now, they will move in fast, and there's a lot of the jungle in computer science right now.
Computer science is not a threat to big energy production. They're
Yeah.
worried about the energy production. That is
Exactly.
the territory that the elites do not want us to go into because they want to control the energy of the world.
Exactly.
Right? Where computer science, it's a free for all. Here's your money, go crazy. And
Yeah.
look at the gains that computer science has made in 20 years. It is fascinating what they've done in 20 years.
The computer scientists created the internet boom in the 90s, and now the AI boom.
AI
And
is just going to
now we're about to change astrophysics. And well, I am about to kick in the butt the astrophysics academia, and
Yeah, like with Phil, I think, like, radio astronomy, it still requires computer science in order to read the values of the data that we're like, let's say the planet is receiving through its little dish, well, that still requires computer science, and still requires, in order to see that wave, that and how far it is, still software. Like, you have to have it to the power of so many, like, what have you reached, the peta, was it the 23 or
oh yeah, but I made a mistake. So I'll talk about that later. It needs to be measured because it's based it's based on the academia theory. It doesn't work. It doesn't work. I tested it already with the liquid metal vortex, and it doesn't work. I'm not getting what the theory predicts at all, by far, by c squared, by the amplitude of the speed of light squared, which is 1 times 10 to the 17.
17? Okay, so 10 to
1 times 10 to the 17, which is a huge factor, a huge difference. And I'm going to talk, well, I might as well talk about it right now, if you don't mind.
No, go ahead.
Yep.
Yeah.
Let her rip. Your little intro. I don't hear any sound. Is there sound in what you're showing? Oh, okay.
Yeah, my speaker don't work. That's why I have earphones and earplugs, sorry. And anyway, but yeah, that's my cool little graph here about the liquid metal vortex, MHD vortex. You can see if you spin it in one way, you're gonna get a gravitational acceleration that is slightly greater than the current one, and if you spin it on the other way, you're gonna get a gravitational acceleration that is slightly lesser than the average one. But what I want to talk about tonight is historical, because nobody is able to figure what gravity is, and it's been like all the brains on the world can't figure out what gravity is. I mean, I did figure it out a while ago, but now I just connected the dots recently in the last week, so that I can put it in the right, using the right words. So if we take the time dilation here, the time dilation, the gravitational time dilation, which is a variation of this equation, but I'm using this one because it's easier to understand. It's actually this is the equation 8 here is the mainstream gravitational time dilation equation, which is exactly the same as this one, but this one is the variation of my theory that is easier to understand. So this is the gravitational time dilation with respect to position. So wherever you are in altitude on Earth, you're gonna have a different time dilation. So according to my theory, the speed is the reciprocal of the time dilation. So wherever you are on Earth, your clock will go at a time rate that is the reciprocal, the inverse of the time dilation. So you're gonna end up with a graph like this. This is where x is the altitude. The blue curve is the time, and the red curve is the speed rate. So you have time rate and speed rate, which is the one is the opposite of the other. So what is the link? And don't forget, time dilation is directly proportional to the energy density. So the closer to the surface of the Earth you are on the left, the greater the energy density will be. So the time rate will be slower, and the speed will be faster because it's the opposite. So so what is the acceleration then? The acceleration is just the differential of the speed. That's all it is. So if we take the acceleration here, which is the differential of the speed, I'm getting this graph, but to get to this graph, I need to add a c-square factor. And if I add the c-square factor, then I get exactly the minus 9.8 meters per second square acceleration on the surface of the Earth. So this is what gravity is. It's the gradient or the differential of the time dilation, and ultimately, and time dilation is proportional to the energy density. It's very simple. Acceleration is it's the you see the speed with respect to position is different. So you take the differential of that, and you get this acceleration curve right here. So it's very simple to understand. It works. It's an equation that works for the Earth, the Sun. This is the acceleration, the gravitational acceleration on the surface of the Sun.
Right. So an example, the gravity on the Sun is going to be a lot greater than Earth.
Yeah.
And we've also proven it too with the size of the moon relative to the Earth. So if you're on the moon, you're going to weigh about 30 to 40% lighter on the moon than you would on the Earth based on the mass of the planet.
Yeah.
And the amount of virtual particles that are bombarding that large body that creates, it's like putting your hand out the window of a car when you're driving. You feel the wind force hitting you. While going through, that's the same thing on the atomic scale with virtual particles going through the universe, and we're traveling on the Earth at 1,000 kilometers an hour rotating, and then our planet is going like over 160,000 miles per hour around the sun. So all that matter that's in space, the Earth is being, is creating almost like a wake with all these particles going through the planet. So our body is physical mass. So if we're getting hit by virtual particles traveling at 120,000 miles per second and hitting us, we don't feel it. We feel gravity, right? They say gravity is one of the weakest forces in the universe by definition. But if you're on a body that's traveling thousands of miles per second through space, those little tiny virtual particles actually amount to something which will create our physical weight. So I don't know if I'm close, or am I off on that? Is that a fair argument, Philip?
I want to ask something.
Yeah, go ahead.
Isn't okay? Like time is dependent on also something called gravity wells and the topography of like our globe, because gravity wells aren't stable. They you know they like it's like a heat signature, like the magma creates gravity wells in certain points. Well, when that happens, our atomic clocks that are on the surface of the earth, this is where the time dilation plays, like so an hour sometimes is not the same as an hour. Some people might feel like, oh, an hour went by so fast, and others might feel like an hour, man, like the hour's not over yet. Well, it has to do with if there's a gravity well underneath, our like underneath the planet, the surface of the earth, you know
Yeah, the gravity well. That's exactly what I'm talking about right here. It's the energy density is denser in the gravity well, and it creates time dilation, and the gradient of that time dilation difference is the acceleration, creates an acceleration. And what I want to say also to Mike is that, and I understand what he's talking about, um, but what I'm talking about here is all relative. I'm not talking. I know the galaxy is moving in the cluster, and the cluster is moving in the supercluster, and supercluster is moving in the universe. I know that very well. I studied that. I worked on that before.
Yeah,
And
because like when you're on a planet, it's all relative to you. We don't feel ourselves moving 1,000 kilometers an hour as there spins. We don't feel it. It feels relative to us because we're on a large body, right? So
yeah,
we don't notice it. And the planet is traveling over 160,000 miles per hour through the universe, going around the sun. So, if 1 year in space, our Earth actually makes one orbit around the sun. We don't feel it. Everything to us, when we're sitting here right now, feels relative. So we
exactly.
don't notice it, right?
Yeah, it's all relative. But I know what you're talking about. If we have something, there's no absolute point in the universe, because if it's consider it's a thought experiment here. If you have a lonely star in an empty universe, can it spin? Can the lonely star spin? No, it can't. It can't spin because it has no frame of reference.
Right.
It creates its own frame of
Exactly.
reference, so it
Right.
can't spin.
It becomes ground zero.
Yeah, exactly. Because it's
It
the
becomes
most
ground
massive.
zero. So
Yeah,
we all know we're not ground zero. So
yeah,
that's where Eric Dollard was correct in his theory, saying, this cup of water or cup of coffee has a lot of energy behind it. So if we were able to have a frame of reference of what we would call zero or ground, okay? So we're traveling through space at 160,000 miles per hour. If I drop this off the train, it's going to make one hell of an explosion. There's so much
yeah,
energy in even our bodies. If we were to go to ground zero, get thrown off the train, we would destroy probably 3 cities. That's how much power is behind us. So,
yeah.
but we don't feel it because everything is relative because we're on a large body. We don't notice us moving through the galaxy, right? We don't feel it. Everything's
Exactly.
relative.
It's all relative.
Right. But
That's,
on the atomic scale, there's a lot of stuff going on,
yeah,
right? The only way we feel it is by physical gravity, right?
exactly.
That's our only reference to know that we have mass is because we feel it, right?
Yeah, exactly.
Bernie's joined us. He's walking around.
Yeah.
Somewhere.
I just want to add also that the C square factor that comes out of nowhere is the exact same factor that I need to add to the gravitomagnetic permeability to get the observed acceleration that the liquid metal vortex we measure. So I need, if we take the theory says that the gravitomagnetic permeability is very weak, but experimentally is very strong because you have to plug in that C square amplitude number that comes out of nowhere, and it's pretty strong. That's why the my liquid vortex MHD liquid metal vortex works. It's because of that C square factor that we need to add, that I need to add to get the right acceleration. So it's a factor that comes out of nowhere, but it works experimentally. It works. It contradicts the physics textbooks, but that's the way it is. You can't argue with the experiments.
Yeah.
What
like the Michelson and Morley experiment that they did, and they said, "Oh, well, the ether drift doesn't exist," and then experiments were carried on later by other engineers, and there is an ether drift. So the ether does exist. I think the ether is very much a big part of what we call gravity.
But that's because the ether for me is the gravito-electric energy layer that is emitted by the Earth, the sun, the moon, the planets. So they're all relative. That's why we can measure it, because it's all relative. But there's a way to measure it, and it's aboard the International Space Station, because it's kind of in between multiple bodies,
Right.
And I already calculated that in my paper.
Yeah, I think, you know what, to prove a lot of these theories, I think half the problem is how the hell do you measure it?
Yeah.
Right? What do we use?
Yeah. And I was accepted by the International Space Station to do my experiment, but they wanted me to pay $500,000. So obviously I don't have that amount of money right now. But
yeah, $500,000 not exactly pocket change.
So yeah, there you go. That's history in the making right here. Nobody is able to explain gravity. I'm telling you what it is. It's the differential of the time dilation. Very simple. And time dilation is proportional to the energy density. Plus, you need to add that C square factor here, and you get the exact same values that are observed. So
very good.
So yeah, that's
awesome. Yeah, that's great. That's a really good. Yeah, I know some people joined late, so later on the show will be posted. So be sure to do a rewind of the beginning of the show, because there's some interesting stuff that we've talked about. And
can you post the Patreon link in the public chat?
Yep, I did your Patreon there. I got it posted. And I also have it up on the screen right now. So if you want to support Philip, you can become part of his Patreon. And also I got my links up there as well.
Yeah, and I just explained to you guys what gravity is. So don't get fooled by these physicists. We don't know what gravity is. It might be it might be gravitons, or it might be the space-time curvature. It's all they can't figure it out. It took them to 100 years, and they still can't figure it out. Yeah. So I'm just telling you what it is right now. So
I think Tesla figured it out too, and there was supposedly a paper he was going to release called his dynamic theory of gravity, but that never came out. It was already too late for Tesla, and he was pretty much shadow banned by the international scientific community at that point. So he was pretty much out of the picture. He was doing a lot of stuff behind the scenes, pretty close to close to when he passed away. But he was pretty much shadow banned, shoved under the rug. I do believe he had some theory written down. It would have been nice if he actually would have published it. I would have liked to have seen that. So it's one of those things we will never know, right? Maybe it was part of those documents that John Trump took from his hotel room after he passed away. Maybe that theory was part of the papers there.
Yeah.
So,
or maybe some of his paper got destroyed or something like that.
I think it just got scooped up by the government. John Trump went through it all and put that paper that he wrote on gravity and put that as top secret. So,
yeah.
Which it wouldn't surprise me if he did.
Yeah. So yeah, thanks for your time. It's
no problem.
It was an intense week this week when I figured it out shortly after your show last week.
Yeah.
And I fine-tuned the equations yesterday.
Right.
And now there you go. So the C-square factor between the experiment and the textbooks are happening in multiple occasions. So don't trust the mainstream too much.
Yeah. Yeah, I think so many people have got discouraged by the academia and what they've done over the last 100 years. And, that Donald Trump it wants some of his stuff that his uncle was working on to come out. And there was actually a hearing on it that they want some of this either anti-gravity stuff coming out or some free energy secrets coming out that Donald Trump's uncle John Trump was working on back in the early part of the 20th century. So, and apparently he's seen some of the stuff. His uncle actually showed him some of the devices he was working on. So Donald Trump was actually a witness to some of this stuff.
Oh, yeah.
So, yeah. So we'll see what happens with that. I hope something comes out. Something. Give us something.
Yeah. Maybe that's why. I'm not gonna name his name, but my good friend from Japan knows Donald Trump, and maybe that's why they're friends, because Trump knows about scientific stuff, apparently, like you said.
Yeah. Oh, he knows there's a lot of stuff that's been withheld. When you have the perfect example, the U.S. Patent Office has well over 3,000 patents that have been seized and put into the drawer because they're free energy or they're going to have something to benefit the planet. And the Patent Office doesn't want that to happen, right? So that's kind of the conspiracy that we're facing here. Getting some of this great tech, out.
Yeah.
So,
what's cracking with did Ben leave or he left?
Ben just disappeared. I don't know what's going on with Mr. Ben. He just kind of disappeared. And then Bernie had to go run an errand with his mother, so he'll be back in a little bit. So
I'm still here. I need to run an errand as well. I need to go pick up my kids.